Tonight, we're going to explore something that might seem like a simple question, but actually breaks the human mind when you truly understand it. Where is the center of the universe? You might think scientists have figured this out by now. After all, we've mapped billions of galaxies, measured the cosmic microwave background, and traced the expansion of space itself. But here's what will twist your brain into knots. The universe has no center. Not because we haven't found it yet. Not because it's hiding somewhere, but because a center literally cannot exist, given how the universe actually works. Every single point in the cosmos has equal claim to being the center. And somehow, impossibly, that means nowhere is. By the end of this journey, you'll understand exactly why, and it will change how you see everything. Before we dive into this cosmic puzzle, if you enjoy these deep explorations of the universe and our place within it, a quick like or subscribe would really help the channel grow. It's a small gesture, but it makes a big difference in bringing these kinds of journeys to more people. Now, let's begin. Let's start with something fundamental about how your brain works. Your mind evolved on Earth, navigating landscapes, tracking prey, avoiding predators, finding shelter, locating water sources. Everything in your daily experience has edges and centers. A rock has a center. A tree has a center. A pond has a center. Your house, your city, your country, all of these things have boundaries and middles. This is so deeply wired into how you think that it feels like a universal truth. Of course, everything has a center. How could anything not have a center? When you think about an explosion, you naturally picture something expanding outward from a central point. Fireworks burst from a single origin. A bomb detonates from one location. A ripple spreads from where the stone hit the water. The center is where it all began, and everything moves away from that point. This mental model is so intuitive, so hardwired into the architecture of your brain, that when scientists talk about the Big Bang, most people immediately picture exactly this. A massive explosion at some specific location in space, with all the matter and energy flying outward from that primordial center. But here's the problem. That picture is completely wrong. Not just a little wrong. Not wrong in some technical sense that doesn't really matter. Fundamentally, deeply, conceptually wrong. And understanding why it's wrong is the key to understanding one of the strangest truths about the cosmos we inhabit. For most of human history, people believed Earth was the center of everything. This wasn't just ignorance or ego, it was a reasonable conclusion based on careful observation. Stand outside on a clear night and watch the sky. The stars appear to wheel overhead in great arcs. The sun rises in the east and sets in the west. The moon follows its own pattern across the heavens. Everything seems to revolve around you, around this place where you're standing. The ancient Greek philosopher Aristotle developed an elaborate cosmology with Earth at the center, surrounded by crystalline spheres carrying the moon, sun, planets, and stars. This geocentric model dominated Western thought for nearly 2,000 years. It wasn't stupid, it matched what people could observe. It made mathematical predictions that were accurate enough for navigation and agriculture. The geocentric model placed Earth at the absolute center of creation. The moon occupied the nearest sphere, orbiting Earth every 27.3 days. Beyond the moon came Mercury, then Venus, then the Sun, then Mars, Jupiter, and Saturn. The outermost sphere carried the fixed stars, completing one rotation every 24 hours. This elegant nested structure made Earth the most important place in existence. We were at the center, and everything else revolved around us. The ancient astronomer Claudius Ptolemy refined this model around 150 AD in his work, The Almagest. He added mathematical devices called epicycles and deference to explain why planets sometimes appeared to move backward in the sky. These weren't just rough approximations. Ptolemy's model could predict planetary positions with reasonable accuracy for centuries. It was a genuine scientific achievement, even if the underlying assumption about Earth's central position was wrong. Then came Nicholas Copernicus in the 16th century. He proposed something radical. What if Earth isn't at the center? What if the Sun is at the center, and Earth orbits around it like the other planets? This heliocentric model was simpler in some ways. It explained the retrograde motion of planets without requiring as many complicated mathematical fixes. When Mars appears to move backward in the sky, it's because Earth is passing Mars in its orbit around the Sun. The apparent backward motion is just a perspective effect, like when you pass a slower car on the highway and it seems to drift backward even though it's still moving forward. But the heliocentric model was controversial. It wasn't just a scientific dispute, it was a philosophical and theological challenge. Removing Earth from the center of creation seemed to diminish humanity's importance. We weren't special anymore. We were just another planet orbiting an ordinary star. The Catholic Church resisted this idea, viewing it as contradictory to Scripture. The Sun was supposed to go around the Earth, not the other way around. Galileo Galilei provided evidence for the heliocentric view in the early 1600s. Through his telescope, he saw moons orbiting Jupiter, proving that not everything orbited Earth. He saw the phases of Venus, which only made sense if Venus orbited the Sun. He saw mountains and craters on the moon, showing it wasn't a perfect celestial sphere. He saw spots on the Sun, showing it wasn't a perfect celestial body. The geocentric model crumbled under the weight of observation. Galileo faced serious consequences for his advocacy of heliocentrism. In 1633, the Roman Inquisition found him guilty of heresy. He was forced to recant his support for the heliocentric model and spent the rest of his life under house arrest. But the evidence was too strong to suppress forever. Within a century, virtually all astronomers accepted that Earth orbited the Sun. But notice what happened. We shifted from thinking Earth was the center to thinking the Sun was the center. The concept of a center remained. We just moved it from Earth to the Sun. Humanity had taken the first step away from the cosmic center. But we hadn't yet questioned whether a center existed at all. Johannes Kepler refined the heliocentric model in the early 1600s. He discovered that planets don't orbit in perfect circles, but in ellipses, with the Sun at one focus. He formulated 3 laws of planetary motion that described exactly how planets move around the Sun. These laws were purely empirical at first. Kepler discovered them by painstakingly analyzing decades of observations, but they were precise and predictive, allowing astronomers to calculate planetary positions far more accurately than the old Ptolemaic system ever could. Then came Isaac Newton in 1687 with his Principia Mathematica. Newton showed that Kepler's laws weren't just patterns in the data. They were consequences of a deeper principle, the law of universal gravitation. Every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. The same force that makes an apple fall from a tree keeps the moon in orbit around Earth and the planets in orbit around the Sun. Newton's physics was revolutionary. It unified terrestrial and celestial mechanics. The same laws that governed falling objects on Earth govern the motions of planets and stars, but Newton's universe still had a conceptual center. He imagined absolute space, a fixed background against which all motion occurred. In this absolute space, you could in principle identify the true center, the point that wasn't moving while everything else moved around it. As telescopes improved, astronomers realized the sun was just one star among many. By the 1800s, they understood that the stars weren't randomly scattered through infinite space. They were organized into a structure, a disk of stars that we see edge on as the Milky Way stretching across the night sky. On clear dark nights, that band of light reveals our galaxy's structure, billions of stars too faint to see individually, but combining into a ghostly glow. But where was the sun in this structure? For a long time, astronomers assumed we were near the center of the Milky Way. This wasn't ego. It was just the default assumption. After all, everything looked roughly similar in all directions when you looked at the distribution of stars. There were about as many stars in one direction as another. It seemed like we were in the middle. This assumption was called the Kaptein universe, named after the Dutch astronomer Jacobus Kaptein, who mapped the galaxy in the early 1900s. Kaptein's model placed the sun near the center of a relatively small galaxy, about 30,000 light-years across. It was a reasonable conclusion based on the data available, but it was wrong. Then, in 1918, astronomer Harlow Shapley studied globular clusters. These are dense spherical collections of ancient stars that orbit the Milky Way like bees around a hive. Each globular cluster contains hundreds of thousands or even millions of stars, packed into a region just a few hundred light-years across. They're among the oldest structures in the galaxy, formed in the first billion years after the Milky Way itself came together. By mapping the positions of globular clusters, Shapley discovered something startling. The globular clusters weren't evenly distributed around us. They were concentrated toward one region of the sky, in the direction of the constellation Sagittarius. If we were at the center of the galaxy, the globular clusters should be spread uniformly in all directions, but they weren't. Most of them were in one direction. This meant the sun wasn't at the center of the Milky Way. We were actually about 26,000 light-years from the galactic center, roughly 2/3 of the way out toward the edge. The sun occupied no special position in our galaxy. It was just another star in the suburbs, orbiting the galactic center along with hundreds of billions of other stars. Once again, humanity had been displaced from the center. First Earth lost its central position in the solar system. Now the sun lost its central position in the galaxy. But the concept of a center still remained. We just weren't at it. The galaxy had a center, even if we weren't there. The pattern of displacement continued, but the underlying assumption of centrality persisted. The next great shift came in the 1920s when Edwin Hubble was studying fuzzy patches of light, called nebulae. Some astronomers thought these nebulae were clouds of gas within the Milky Way. Others thought they might be separate galaxies, island universes far beyond our own. The debate was fierce and unresolved. Using the 100-inch telescope at Mount Wilson Observatory in California, Hubble resolved individual stars in some of these nebulae. He identified Cepheid variable stars, which pulsate with a period related to their intrinsic brightness. A Cepheid that pulses every 10 days has a certain luminosity. A Cepheid that pulses every 30 days is brighter. By measuring the pulsation period, Hubble could calculate how bright the star actually was. Then, By comparing that intrinsic brightness to how bright the star appeared, he could calculate how far away it was. The results were staggering. These nebulae weren't clouds of gas within the Milky Way. They were entire galaxies, collections of billions of stars, located millions of light years away. The Andromeda Nebula, visible to the naked eye as a faint smudge on clear dark nights, turned out to be a spiral galaxy containing roughly 1 trillion stars, located about 2.5 million light years from us. The universe suddenly became vastly larger. The Milky Way wasn't the whole cosmos. It was just one galaxy among many. Astronomers soon realized there were millions of galaxies, then billions, then trillions, scattered throughout space as far as telescopes could see. Each galaxy was a vast collection of stars, many larger than the Milky Way, spread through a volume of space almost incomprehensibly vast. But Hubble discovered something even more profound. When he measured the light from distant galaxies, he found it was shifted toward the red end of the spectrum. This redshift indicated the galaxies were moving away from us. Light waves stretch when their source is moving away, just like the pitch of a siren drops as an ambulance speeds past you. The faster the source moves away, the more the waves stretch, the redder the light becomes. And there was a pattern. The farther away a galaxy was, the faster it was receding. A galaxy twice as far away was moving away twice as fast. A galaxy 10 times farther was moving away 10 times faster. This became known as Hubble's law, and it revolutionized our understanding of the cosmos. At first glance, this seemed to restore Earth to the cosmic center. If everything is moving away from us, doesn't that mean we're at the center of some cosmic expansion? Aren't all those galaxies fleeing from our location specifically? Didn't Hubble's discovery prove that we were at the center after all? No. And here's where things get genuinely strange. Here's where the intuitive concept of a center finally breaks down completely. Here's where everything you thought you knew about space and geometry fails to apply. Imagine you're an astronomer on a planet in the Andromeda Galaxy, 2.5 million light years from the Milky Way. You build a telescope and measure the motion of distant galaxies. What do you find? Exactly the same thing Hubble found. All the distant galaxies are moving away from you. The farther away they are, the faster they're receding. From the Andromeda astronomer's perspective, their galaxy appears to be at the center of the expansion. Now imagine an astronomer in a galaxy 1 billion light years away. They measure distant galaxies and find the same pattern. Everything is moving away from them. They appear to be at the center too. In fact, no matter which galaxy you choose, no matter where in the universe you make your observations, you will always find that distant galaxies are receding from your position. Everyone observes the same pattern. Everyone appears to be at the center of the expansion. But if everyone is at the center, then no one is at the center. The concept of center loses meaning. It's not that we haven't found the center yet. It's not that the center is hidden somewhere and we just need better telescopes. It's that the very concept of a center doesn't apply to the universe as a whole. This is not a paradox or a logical contradiction. It's a consequence of how the universe actually works. The expansion of the universe is not galaxies flying through space away from some central point. The expansion is the stretching of space itself. The fabric of space is getting larger, and everything embedded in that fabric is being carried along with it. Think about what this means. Space isn't a pre-existing container that the universe is exploding into. Space is part of the universe. When the universe expands, It's space itself that's expanding. New space is being created everywhere, all the time, at every point in the cosmos. This is fundamentally different from an explosion, where debris flies through pre-existing space, away from an origin point. This is why there's no center. An explosion has a center because stuff is moving through pre-existing space, away from an origin point. But the expansion of the universe isn't stuff moving through space. It's space itself getting bigger. And space doesn't have a center. It's not expanding into anything. It's just expanding. Let me try to make this more concrete with an analogy. Imagine you're an ant living on the surface of a balloon. Your entire universe is that two-dimensional surface. You can move forward, backward, left, right, but you have no concept of up or down. The surface of the balloon is everything that exists from your perspective. Now imagine the balloon starts inflating. As it gets bigger, the distance between any 2 points on the surface increases. If you're an ant and you look at other ants scattered across the balloon, you'll see them all moving away from you. The farther away an ant is, the faster it appears to be receding. But here's the crucial insight. There's no center on the surface of the balloon. The balloon's surface is curved and finite, but it has no edges and no center. Every point on the surface is equivalent. No ant can claim to be at the special center of the expansion. Every ant observes the same pattern of everything moving away. Now, you might object that the balloon does have a center. It's the center of the balloon, the point in the middle of the three-dimensional sphere. But that point isn't on the surface. The ant's universe is the surface only. The center of the balloon exists in a higher dimension that the surface-dwelling ants cannot access or even perceive. It's outside their universe entirely. They can't point to it. They can't travel to it. For all practical purposes, from the ant's perspective, it doesn't exist. In our universe, the situation is similar but more complex. Our three-dimensional space might be curved in a way that exists in a higher dimension we cannot perceive. There might be no center at all, or if there is something analogous to a center, it's not anywhere in our three-dimensional space. It's outside our universe entirely, in a direction we cannot point, in a dimension we cannot access. This is why asking where is the center of the universe is like asking what's north of the North Pole. The question seems sensible on the surface. It uses words that have meaning in other contexts. But it's actually malformed. It assumes a framework that doesn't apply. There is nothing north of the North Pole because north is defined as the direction toward the North Pole. Once you're there, the concept of north no longer makes sense. Similarly, there is no center of the universe because the universe doesn't have the kind of geometry where center is a meaningful concept. The Big Bang wasn't an explosion in space, it was an expansion of space. It didn't happen at some location in the universe. It happened everywhere in the universe simultaneously. Every point in space was the location of the Big Bang. Every point has equal claim to being where it all began. When scientists say the universe is about 13.8 billion years old, they don't mean there's a location that's 13.8 billion light years away where the Big Bang happened. They mean that 13.8 billion years ago, the universe was in a very different state. It was incredibly hot, incredibly dense, and incredibly small. But it wasn't a small region of space surrounded by emptiness. The entire universe, all of space, was compressed into that hot, dense state. There was no outside. There was no empty space around it. It was everything. As the universe expanded, space stretched. New distance appeared between objects. Matter cooled and clumped together under gravity. Eventually, galaxies formed, stars ignited, planets coalesced, and the expansion continues today, with space stretching and carrying galaxies apart from each other. This is fundamentally different from an explosion. In an explosion, there's a before and after in terms of space. Before the bomb detonates, there's space where the explosion will occur. After the detonation, stuff spreads out through that pre-existing space. But in the expansion of the universe, there is no pre-existing space. Space is being created. The universe isn't expanding into anything. There's no empty void outside the universe that it's spreading into. The universe is all there is. This makes the question, where is the center, a category error. It's like asking what color is the number 7 or how much does Wednesday weigh. The question assumes something that isn't true, that the universe has a geometric center the way a sphere or a cube does. But the universe isn't a sphere or a cube, sitting in some larger space. It is all of space. And all of space doesn't have a center in any meaningful sense. Some people find this explanation unsatisfying. They want to know where the Big Bang happened. They want coordinates. They want to be able to point in a direction and say, the origin is that way. But the answer is that the Big Bang happened here, and everywhere. It happened at every point in space. Because in the beginning, every point that exists today was compressed together in that initial state. You are at the center of where the Big Bang happened. So is every galaxy in the universe. So is every empty void between the galaxies. The Big Bang happened at all of those locations because there was no distinction between those locations 13.8 billion years ago. They were all the same place, or so close together that the distinction is meaningless. This is why the universe has no center. Not because we haven't found it, not because it's hidden, but because the very nature of cosmic expansion makes the concept inapplicable. Every location is equally valid as the center. Every observer, anywhere in the universe, sees themselves as the center of the expansion. And when everywhere is the center, nowhere is. Understanding this requires letting go of deeply ingrained intuitions about space and geometry. Your brain evolved to understand rocks and ponds and landscapes, not curved four-dimensional space-time. The mental models that served your ancestors well on the African savannah millions of years ago don't work when contemplating the structure of the cosmos. But with enough effort, with enough different analogies and explanations, you can build a new intuition. You can understand why the universe is centerless without feeling like you're missing something. The journey from geocentrism to heliocentrism to our modern understanding took centuries. Each step displaced humanity a little further from the cosmic center. First, Earth wasn't at the center of the solar system. Then the sun wasn't at the center of the galaxy. Then the galaxy wasn't at the center of the universe. And finally, we realized there is no center at all. Each step was resisted. Each step felt like a diminishment. But each step also revealed a universe more vast, more complex, and more wonderful than the one before. The geocentric universe was small and simple. The heliocentric universe was larger. The modern universe is almost incomprehensibly vast, containing trillions of galaxies spread across billions of light years. And once you truly grasp this, the universe becomes even more wonderful. Not smaller, not diminished, but stranger and more marvelous than any human culture ever imagined. A cosmos without edges, without a center, without an outside. Just existence, expanding eternally into itself, governed by physical laws that make no distinction between one place and another. Every point equivalent. Every observer equally at the center and equally not at the center. A democracy of locations in an infinite expanse. Now that we've begun to grasp why our intuitions about centers fail at cosmic scales, let's go deeper into the mechanics of cosmic expansion. Because understanding exactly how the expansion works is crucial to truly accepting the centerless nature of our cosmos. This isn't just an abstract philosophical point. The expansion of the universe has been measured with extraordinary precision, and those measurements tell us something profound about the nature of space itself. When Edwin Hubble discovered that distant galaxies were moving away from us, he didn't just notice they were moving. He discovered a precise mathematical relationship that would revolutionize cosmology. The speed at which a galaxy recedes is directly proportional to its distance from us. A galaxy twice as far away moves twice as fast. A galaxy 10 times farther moves 10 times faster. A galaxy 100 times farther moves 100 times faster. This relationship is now called Hubble's law, and it's one of the most important discoveries in the history of science. Current measurements tell us that for every megaparsec of distance, a galaxy's recession velocity increases by somewhere between 67 and 73 kilometers per second, depending on the measurement method. A megaparsec is about 3.26 million light years. So a galaxy 3.26 million light years away is receding at roughly 70 kilometers per second. A galaxy 6.52 million light years away is receding at roughly 140 kilometers per second. A galaxy 32.6 million light years away is receding at roughly 700 kilometers per second. And so on, scaling perfectly with distance. Interestingly, different measurement techniques give slightly different values for this expansion rate. Measurements using the cosmic microwave background give lower values, while measurements using Cepheid variable stars and supernovae give higher values. Scientists call this discrepancy the Hubble tension, and resolving it is one of the active frontiers of cosmological research. Either one set of measurements has a subtle error we haven't found, or there's new physics we don't yet understand. This expansion rate, whatever its precise value, is called the Hubble constant. It tells us the rate at which the universe is expanding right now, and it applies uniformly throughout space. Everywhere in the universe, at every point, the expansion follows the same law. There's no region where the Hubble constant is different. There's no direction where galaxies recede faster or slower than this relationship predicts. The expansion is remarkably uniform. Now, here's where things get interesting. Hubble's law seems to put us at the center. If everything is moving away from us, if the recession velocity depends on distance from us, doesn't that make our position special? How can this be consistent with no center? This seems like a contradiction. Either we're at the center or we're not. How can we observe everything moving away from us and still claim we're not in a special location? The key insight is that Hubble's law looks exactly the same from every vantage point in the universe. Let me explain why with a thought experiment that will make this crystal clear. Imagine a very long ruler, one that stretches across billions of light years. This ruler has marks on it every million light years. Now, imagine space starts expanding uniformly. Every part of the ruler stretches by the same percentage. Let's say space expands by 10%. A section of the ruler that was 10 million light years long becomes 11 million light years long. A section that was 100 million light years long becomes 110 million light years long. A section that was 1 billion light years long becomes 1.1 billion light years long. Notice what happened. The 10 million light year section grew by 1 million light years. The 100 million light year section grew by 10 million light years. The billion light year section grew by 100 million light years. The stretching is proportional to the original length. Longer sections stretch more in absolute terms, even though the percentage is the same everywhere. Now imagine you're standing at one end of this ruler and you look toward the other end. A mark that was 10 million light years away is now 11 million light years away. It has moved 1 million light years away from you in whatever time it took for the expansion to happen. A mark that was 100 million light years away is now 110 million light years away. It has moved 10 million light years away from you in the same time. That's 10 times the distance gained for 10 times the original separation. This is Hubble's law. The recession velocity is proportional to distance. But notice that this has nothing to do with where you're standing on the ruler. Pick any point on the ruler and measure distances from there. You'll find the same relationship. Farther marks move away faster in direct proportion to their distance. Every point on the ruler observes the same Hubble's law. Every point appears to be at the center of the expansion. This is exactly what happens in the expanding universe. Space is stretching uniformly everywhere. Every point sees distant galaxies receding with velocities proportional to distance. No point is special, no point is the center. The Hubble's law relationship is a consequence of uniform expansion, not evidence for a central position. Let me make this even more concrete with another analogy that might help solidify this concept. Imagine a loaf of raisin bread dough. Before baking, the raisins are scattered through the dough at various distances from each other. Each raisin represents a galaxy. The dough represents space itself. Now put the dough in the oven. As it bakes, the dough expands uniformly in all directions. Every part of the dough is rising, stretching, growing. Pick any raisin and call it Raisin A. This is us, the Milky Way. Look at another raisin, Raisin B, that was originally 1 centimeter away. After the dough doubles in size, Raisin B is now 2 centimeters away. It has moved 1 centimeter away from Raisin A during the baking time. Now look at Raisin C, which was originally 5 centimeters away from Raisin A. After the dough doubles, Raisin C is now 10 centimeters away. It has moved 5 centimeters away from Raisin A in the same amount of baking time. From Raisin A's perspective, Raisin C moved 5 times farther than Raisin B in the same amount of time. Raisin C is receding faster. The recession speed is proportional to the original distance. This is Hubble's law in raisin form. But here's the crucial point. Pick any other raisin as your reference point. Do the same measurements from Raisin D's perspective, or Raisin E's, or Raisin F's, or any raisin in the loaf. You'll find exactly the same relationship. Everything is moving away from that raisin too. The recession speeds are proportional to distance from that raisin too. No raisin is at the center. No raisin is special. The expansion is the same from every perspective. The universe is like the dough. Galaxies are like the raisins. Space is stretching uniformly, carrying the galaxies along with it. Every galaxy sees the same Hubble's law. Every galaxy appears to be at the center of the expansion, and therefore no galaxy is actually at the center. The appearance of centrality is universal. which means it indicates nothing special about any particular location. Now, there's an important subtlety here that many people find confusing. When we say galaxies are moving away from us, we don't mean they're flying through space like rockets zooming away from a launch pad. We mean the space between us and them is stretching, creating more distance over time. The galaxies themselves might be essentially stationary in their local region of space. They're not firing engines or being pushed by any force. They're just sitting there while the space between us and them grows. This distinction matters enormously. If galaxies were flying through space, they would have velocities that could be compared to the speed of light. Einstein's theory of special relativity tells us that nothing can move through space faster than light. That's one of the most fundamental laws of physics, confirmed by countless experiments over more than a century. The most distant galaxies we can observe have recession velocities that exceed the speed of light. Some galaxies are receding at 2 or 3 times the speed of light. If their recession were true motion through space, this would violate Einstein's theory. It would be impossible. The universe would be breaking its own rules. So how can distant galaxies appear to be receding faster than light? Because they're not moving through space faster than light. They're essentially stationary in their local patch of space. It's the space between us and them that's expanding, and there's no speed limit on how fast space can expand. The expansion of space is not motion through space. It's a different phenomenon entirely, governed by different rules. Think about it this way. Imagine 2 ants on a rubber band. The ants are standing still, not walking at all. But you start stretching the rubber band. The distance between the ants increases, even though neither ant is moving. If you stretch the rubber band fast enough, the distance between the ants could increase faster than any ant could ever walk. But neither ant is violating any speed limit because neither ant is walking. The increase in distance is happening because the rubber band is stretching, not because the ants are walking. The universe works the same way. Distant galaxies are essentially stationary in their local space. They might have small, peculiar velocities of a few hundred kilometers per second due to local gravitational influences. Galaxies and clusters orbit each other. Galaxies fall toward nearby concentrations of mass. These local motions are real motion through space, and they're always slower than light. But the large-scale recession, the part that makes distant galaxies appear to zoom away at tens of thousands or hundreds of thousands of kilometers per second, is not motion through space. It's space itself expanding. This has profound implications for the question of the universe's center. If galaxies were flying away from a central explosion point, the fastest ones would be the ones that got the biggest push. There would be an asymmetry. The galaxies flung in one direction might have different speeds than those flung in another direction. We could potentially trace the trajectories back and find the origin point. The way you can trace the paths of firework debris back to where the rocket exploded. But if galaxies are being carried by expanding space, there's no such asymmetry. Every region of space is expanding in the same way. There's no trace of an origin point because there was no origin point in the conventional sense. The expansion is happening everywhere, uniformly, all the time. You can't trace it back to a location because every location is equally the source of the expansion. Let's talk about how we actually measure this expansion. The primary tool is redshift. When light travels through expanding space, its wavelength gets stretched along with the space. Longer wavelengths mean the light looks redder than it originally was. Blue light becomes green, green becomes yellow, Yellow becomes orange, orange becomes red, red becomes infrared. By measuring how much the light from a distant galaxy has been redshifted, we can determine how much space has expanded since the light was emitted. Here's how it works in practice. Every element in the periodic table emits and absorbs light at specific wavelengths. These are called spectral lines. Hydrogen, for example, has a distinctive pattern of lines. One line at 656 nanometers, another at 486 nanometers, another at 434 nanometers. This pattern is like a fingerprint. No matter where hydrogen is in the universe, it produces this same pattern. When astronomers look at the light from a distant galaxy, they can identify these patterns. They see the hydrogen fingerprint, but the patterns are shifted to longer wavelengths. If hydrogen's lines appear at twice their normal wavelengths, with the 656 nanometer line now appearing at 1312 nanometers, we know space has doubled in size since that light was emitted. The light has been traveling through expanding space, stretching as it goes, until it arrives at our telescopes with wavelengths twice as long as when it started. The cosmic microwave background radiation provides powerful additional evidence for cosmic expansion. This ancient light, released when the universe was only 380,000 years old, has been stretched by cosmic expansion from visible light into microwaves. We'll examine this evidence in detail when we explore the cosmological principle in the next section. Now, you might wonder if the expansion is slowing down or speeding up. After all, gravity pulls things together. You might expect all the mass in the universe to be gravitationally slowing the expansion over time, like a ball thrown upward that gradually slows as Earth's gravity pulls it back. Eventually, you might think the expansion would stop and reverse, leading to a big crunch where everything falls back together. For most of the 20th century, cosmologists assumed this was the case. The expansion should be decelerating. The question was whether it was decelerating fast enough to eventually stop and reverse, leading to a big crunch, or slowly enough that the expansion would continue forever, albeit more and more slowly, leading to a cold, empty universe spreading out forever. Then, in 1998, two independent teams of astronomers made a shocking discovery that would ultimately win them the Nobel Prize in Physics. The discovery came from two competing groups working independently. The Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, had been hunting distant supernovae since 1988. The High Z Supernova Search Team, led by Brian Schmidt in Australia with Adam Rees, analysing the data at Berkeley, started their search in 1994. Both teams were using the same technique. They hunted for Type 1a supernovae in distant galaxies. These are exploding white dwarf stars that all reach roughly the same peak brightness, making them excellent standard candles for measuring cosmic distances. If you know how bright something actually is, and you measure how bright it appears, you can calculate how far away it is. Both teams expected to find deceleration. That's what gravity should do. That's what every cosmologist assumed. The universe was full of matter, and matter has gravity, and gravity should slow the expansion. The only question was, how much? Was the universe dense enough to eventually halt the expansion and collapse? Or was it sparse enough to expand forever at an ever-slowing rate? When the data came in, both teams thought they had made a mistake. The distant supernovae were fainter than they should have been, not brighter as decelerating expansion would predict, but fainter. This meant the supernova were farther away than expected. The universe had expanded more than it should have if gravity were slowing things down. Both teams checked their data obsessively. They looked for errors. They looked for dust that might be dimming the supernovae. They looked for any explanation other than the obvious one. But the data held firm. The expansion of the universe wasn't decelerating. It was accelerating. The two teams announced their results within weeks of each other in early 1998. The scientific world was stunned. Something was pushing the universe apart, making space expand faster and faster over time. This mysterious something was dubbed dark energy, and it makes up about 68% of the total energy content of the universe. We still don't know what dark energy is. It's one of the biggest mysteries in modern physics. Dark energy might be a property of space itself, what physicists call a cosmological constant. Einstein actually proposed such a constant in 1917, then reportedly abandoned it when Hubble discovered the expansion of the universe, believing it was no longer needed. But it turns out Einstein might have been onto something after all, just for different reasons than he originally thought. The cosmological constant would mean that empty space has energy. Every cubic meter of space, even completely empty space with no matter or radiation in it, would contain a tiny amount of energy. As space expands and more space is created, more of this energy appears. This energy has a repulsive gravitational effect, pushing space apart, causing more expansion, creating more space, creating more energy, causing more expansion. It's a runaway process that will continue forever. Alternatively, dark energy might be some new kind of field that pervades the universe, something physicists call quintessence. This field would have the property of pushing things apart rather than pulling them together like gravity does. It might be something even stranger that we haven't yet conceived. The honest answer is that we don't know what dark energy is. We know it exists because we can measure its effects, but its fundamental nature remains one of the deepest mysteries in science. Whatever dark energy is, it's causing the expansion of the universe to speed up. And this has implications for the question of a cosmic center. An explosion decelerates due to gravity and air resistance. The fastest particles get slowed down the most. Over time, you could study the debris pattern and potentially trace it back to an origin. But an expansion driven by dark energy doesn't work that way. Dark energy is a property of space itself. It exists everywhere, in every cubic meter of the void, uniformly distributed throughout the cosmos. There's no concentration, no gradient, no center. It's the same at every point in space. This means the acceleration of the expansion is the same everywhere. No location is special, no location is the center of the acceleration, just as no location is the center of the expansion. Let me return to the question of perspective. I've said that every observer sees themselves at the center of the expansion. Let's explore what that actually means with a concrete example. Imagine you're in a galaxy 1 billion light years away from Earth. You look out at the universe with your telescope. In one direction, you see the Milky Way. It's redshifted, moving away from you at about 70,000 kilometers per second, based on Hubble's law. In the Boise opposite direction, you see a galaxy 2 billion light years away from the Milky Way. This galaxy is also moving away from you. Now, from our perspective on Earth, that second galaxy is moving away from us at about 140,000 kilometers per second, twice the speed of the first galaxy, the one where you're standing. This makes sense because it's twice as far away. But from your perspective in that middle galaxy, what do you see? The Milky Way is moving away from you at 70,000 kilometers per second in one direction. The second galaxy is moving away from you at 70,000 kilometers per second in the opposite direction. Both galaxies are receding from you. You appear to be at the center. What's happening is this. The Milky Way is moving away from you because of the expansion between your galaxy and the Milky Way. The second galaxy is moving away from you because of the expansion between you and it. The velocities don't add up the way you might expect from everyday experience because we're not talking about motion through space. We're talking about space expanding. This is a consequence of the mathematics of uniform expansion. If space is stretching uniformly everywhere, the recession velocities necessarily work out in a way that preserves Hubble's law from every perspective. It's not a coincidence. It's not an accident. It's a mathematical inevitability that follows from the assumption of uniform expansion. Some people find this hard to accept intuitively. They think there must be some way to figure out which perspective is the true one. Surely one observer is really at the center and the others are just mistaken. But there isn't any way to determine this. The expansion of the universe is fundamentally symmetric. Every point is equivalent. There is no true center from which the expansion is really happening. Every observer's perspective is equally valid. None is more correct than any other. This is closely related to a principle in physics called the Copernican principle, named after Copernicus, who moved Earth from the center of the cosmos. The Copernican principle states that we don't occupy a special place in the universe. There's nothing unique about our location. Any other location would observe the same basic physical laws and the same large-scale structure. Modern cosmology takes this further with the cosmological principle, which states that on large enough scales, the universe is the same everywhere and the same in all directions. We'll explore this in detail in the next section, but for now, the key point is that these principles are not just philosophical assumptions. They're supported by observations. The universe really does look the same from everywhere, as far as we can tell. The expansion of the universe is happening right now as you listen to these words. Every second, the distance between distant galaxies and us is increasing. Space is stretching, new space is being created everywhere. This isn't some event that happened long ago and is now finished. It's an ongoing process, continuous and perpetual, accelerating into the future. The nearest large galaxy, Andromeda, is actually getting closer to us, not farther away. This is because Andromeda is close enough that local gravitational attraction overcomes the cosmic expansion. The Milky Way and Andromeda are falling toward each other at about 110 kilometers per second, destined to eventually merge. But beyond our local group of galaxies, the expansion dominates. The Virgo cluster, a massive collection of over 1,000 galaxies about 54 million light-years away, is receding from us at about 1,200 kilometers per second. The Coma cluster, about 330 million light-years away, is receding at about 7,000 kilometers per second. These clusters contain thousands of galaxies, trillions of stars, and they're all being carried away from us by the expansion of space. This accelerating expansion has profound implications for the far future of the cosmos. Eventually, distant galaxies will be carried beyond our cosmic horizon forever. Their light no longer able to reach us across the ever-widening gulf of expanding space. We'll explore what this means for future observers later in our journey. Understanding the expansion of the universe, truly understanding it, requires letting go of the intuitive picture of an explosion in space. The universe is not stuff moving through pre-existing space away from some origin point. The universe is space and stuff together, expanding as one. The expansion is not happening at the edge of something. It's happening everywhere, at every point, all the time. And because it's happening everywhere equally, there is no center. The concept simply doesn't apply. Every galaxy is receding from every other galaxy. Every observer sees the same Hubble's law. Every observer appears to be at the center. And when everyone is at the center, no one is at the center. This is not a paradox. It's not a contradiction. It's just how uniform expansion works. It's a mathematical consequence of space stretching equally everywhere. The universe expands, space stretches, galaxies drift apart, and nowhere in all that vast expanding cosmos is there a point you can identify as the center. Not because we haven't looked hard enough, not because the center is hidden, but because the very nature of uniform expansion makes such a point impossible. The center is everywhere and nowhere. Every point is equally central and equally peripheral. And that's exactly how a universe without a center should be. We've established that the expansion of the universe looks the same from every vantage point. But this is just one aspect of a deeper truth about the cosmos. At the larger scales, the universe is remarkably uniform. This uniformity is what makes the centerless nature of the cosmos not just possible, but inevitable. To understand why, we need to explore two related concepts that form the foundation of modern cosmology: homogeneity and isotropy. Together, they form what cosmologists call the cosmological principle. And understanding this principle is essential to grasping why the universe cannot have a center. Let's start with isotropy. Isotropy means the same in all directions. An isotropic universe looks the same no matter which direction you look. If you were floating in deep space and observed the distribution of galaxies in every direction, an isotropic universe would show no preferred direction. There would be no direction where galaxies are systematically more clustered, or moving faster, or younger, or older. North, south, east, west, up, down, all directions would be equivalent. Now, at small scales, the universe is definitely not isotropic. If you look toward the constellation Virgo, you see a massive concentration of galaxies, over 1,000 of them bound together by gravity about 54 million light years away. If you look in the opposite direction, toward the constellation Leo, you see a different arrangement of galaxies entirely. The local universe is lumpy and asymmetric. There are clusters and voids, walls and filaments. Structure is everywhere at these scales. Stand on Earth and look around. In one direction you see the sun, in another direction you see the moon, in yet another direction you see the dense band of the Milky Way stretching across the sky. These directions are clearly different from each other. The universe at human scales, at solar system scales, even at galactic scales, is highly anisotropic. But if you zoom out far enough, these local variations average out. Look at scales of hundreds of millions of light years or more, and the universe becomes remarkably smooth. The density of galaxies is roughly the same in every direction. The expansion rate is the same in every direction. The temperature of the cosmic microwave background radiation is the same in every direction to about 1 part on 100,000. This isotropy is a powerful constraint on the structure of the universe. If the universe is isotropic, it cannot have a center in any meaningful sense. A center would be a special point, and there would be a preferred direction pointing toward or away from that center. every observer would be able to determine which direction leads toward the center and which direction leads away from it. But isotropy rules this out. All directions are equivalent. There is no preferred direction, which means there can be no center to point toward. Now, let's consider homogeneity. Homogeneity means the same everywhere. A homogeneous universe has the same properties at every point in space. The density of matter is the same everywhere. The laws of physics are the same everywhere. The age of the universe, measured from the Big Bang, is the same everywhere. No location is special or different from any other location. Again, at small scales, the universe is not homogeneous. We live on a planet which is vastly denser than the space between planets. Our planet orbits a star, which is denser still. Our star is in a galaxy, which is far denser than the vast voids of intergalactic space. Our galaxy is in a supercluster, which is part of the cosmic web of filaments and voids that spans the observable universe. The density of matter varies enormously from place to place at these scales. Inside a star, matter is packed incredibly densely. In the space between galaxies, there might be only one atom per cubic meter. The difference in density between a stellar core and intergalactic space is about 30 orders of magnitude. That's a 1 followed by 30 zeros. The universe at small scales is extraordinarily lumpy, but at large enough scales, typically above about 300 million light years, the universe smooths out. The cosmic web averages into a uniform density. There are no super clusters. There's no systematic repeating pattern at scales larger than about 1 billion light years. Individual large structures exist, but they're randomly distributed, and the universe becomes statistically uniform at these scales. There's just a roughly uniform distribution of matter throughout the observable universe, with random variations that average to zero. Homogeneity rules out a center even more directly than isotropy. If every point in the universe is equivalent, then no point can be a special center. A center would have to be different from other points. Perhaps it would be denser or older or at the origin of the expansion. But homogeneity means all points are the same. There's no basis for picking one point as the center because there's nothing to distinguish it from any other point. The combination of homogeneity and isotropy is called the cosmological principle. It states that on large scales, the universe is both the same everywhere and the same in all directions. This principle has been assumed by cosmologists since the early 20th century, but it's not just an assumption anymore. We have strong observational evidence that it's true. The most spectacular evidence comes from the cosmic microwave background radiation, or CMB. This is radiation left over from the early universe, emitted about 380,000 years after the Big Bang. Before that time, the universe was so hot that atoms couldn't form. Electrons roamed freely, constantly scattering photons of light, making the universe opaque. Light couldn't travel more than a short distance before hitting an electron and bouncing off in a random direction. But as the universe expanded and cooled, the temperature dropped below about 3,000 degrees. At this temperature, electrons could finally combine with protons to form neutral hydrogen atoms. Suddenly, light could travel freely without being scattered. The universe became transparent for the first time. Photons that had been bouncing around in the hot plasma were suddenly free to travel in straight lines across the cosmos. The light that was released at that moment has been traveling through space ever since, for 13.8 billion years. As the universe expanded, this light was stretched, its wavelength increasing from visible light to infrared to microwaves. Today, it fills all of space as a faint glow of microwave radiation, coming from every direction, corresponding to a temperature of about 2.7 degrees above absolute zero. In 1965, Arno Penzias and Robert Wilson accidentally discovered this radiation while working with a radio antenna at Bell Telephone Laboratories in New Jersey. They were trying to use the antenna for satellite communication experiments, but they kept detecting a faint hiss that they couldn't eliminate. They checked the equipment. They cleaned pigeon droppings off the antenna. They pointed it in different directions. Nothing worked. The hiss was always there, constant and uniform, coming from every direction in the sky. They had discovered the cosmic microwave background. This accidental discovery would win them the Nobel Prize in Physics and provide the strongest evidence for the Big Bang Theory. The CMB is the afterglow of creation, the oldest light in the universe, a snapshot of the cosmos when it was only 380,000 years old. Since then, satellites like COBE, WMAP, and Planck have mapped the CMB with exquisite precision. The COBE satellite, launched in 1989, made the first detailed measurements from space. WMAP, launched in 2001, dramatically improved both the precision and angular resolution, revealing fine details invisible to COBE. Planck, launched in 2009, improved the measurements further still, mapping the CMB with unprecedented accuracy. These missions have given us an incredibly detailed picture of the early universe. What they found is astonishing. The CMB is almost perfectly uniform across the entire sky. The temperature varies by only about 1 part in 100,000 from one direction to another. This is like measuring the temperature of a room and finding it's the same everywhere to within 1,000th of a degree. The precision of this uniformity is remarkable. This means the universe at the time the CMB was emitted was incredibly smooth. The same temperature everywhere means the same density everywhere. Homogeneity and isotropy confirmed to extraordinary precision. The universe 380,000 years after the Big Bang was almost perfectly uniform, with no center, no edge, no preferred direction. Those tiny 1 part in 100,000 variations are important though. They're the seeds from which all structure grew. Regions that were slightly denser than average attracted more matter through gravity. Over billions of years, these regions became galaxies and galaxy clusters. The cosmic web of filaments and voids we see today grew from those tiny primordial fluctuations. If there were no fluctuations, if the early universe had been perfectly uniform, no structure would ever have formed, galaxies wouldn't exist, stars wouldn't exist, planets wouldn't exist, you wouldn't exist. Those tiny variations, just 1 part in 100,000, were essential for creating the complex universe we see today. The pattern of these fluctuations also tells us something profound. They're random. There's no preferred scale, no special pattern, no hint of a center or edge. The fluctuations are what physicists call Gaussian, meaning they follow a random statistical distribution with no preferred location or direction. This is exactly what you'd expect from quantum fluctuations in the very early universe, stretched to cosmic scales by inflation. Inflation is a theory that proposes the universe underwent a brief period of exponentially rapid expansion in the first tiny fraction of a second after the Big Bang. During inflation, the universe expanded by a factor of at least 10 to the power of 26 in about 10 to the power of negative 32 seconds. This is an almost incomprehensibly rapid expansion. A region smaller than an atom expanded to something larger than the observable universe today. Inflation explains why the universe is so uniform. Before inflation, the universe was small enough that different regions could communicate and equilibrate. Everything was in contact with everything else. Then inflation stretched this tiny uniform region to cosmic scales. The uniformity we see today is a relic of that early equilibrium, preserved by the rapid expansion. Inflation also explains the origin of the fluctuations. Quantum mechanics tells us that empty space isn't really empty. It's filled with tiny quantum fluctuations, virtual particles popping in and out of existence. During inflation, these microscopic quantum fluctuations were stretched to macroscopic scales. They became the seeds of cosmic structure, the 1 part in 100,000 variations we see in the CMB. If there were a center to the universe, you might expect to see some imprint of it in the CMB. Maybe the fluctuations would be systematically different in one direction, pointing toward or away from the center. Maybe there would be a gradient with hotter or colder temperatures in one region. Maybe there would be a pattern, circles or lines, or some other structure that revealed the center's location. But we see nothing like that. The CMB is isotropic to an astounding degree, with only random fluctuations superimposed. The fluctuations show no preferred direction. They show no evidence of a center. They're consistent with a universe that is the same everywhere, with no special locations. Let me discuss some other evidence for the cosmological principle. Galaxy surveys have mapped the distribution of millions of galaxies across the observable universe. Projects like the Sloan Digital Sky Survey, the 2-degree field Galaxy Redshift Survey, and the Dark Energy Survey have measured the positions and distances of galaxies in enormous volumes of space. The Sloan Digital Sky Survey alone has measured the positions and properties of over 3 million galaxies, along with spectra that reveal their distances. This allows astronomers to build 3-dimensional maps of the universe, showing where galaxies are located in space, not just where they appear on the sky. What they've found is that on scales larger than about 300 million light years, the distribution of galaxies is remarkably uniform. There are no superhuge structures that dominate the cosmos. The cosmic web of filaments and voids averages out to a smooth density. Homogeneity is confirmed. These surveys also show isotropy. The distribution of galaxies looks the same in different directions, once you account for local variations. The northern sky has about the same galaxy density as the southern sky. The direction toward Virgo has about the same galaxy density as the direction toward Leo, averaged over large enough volumes. There's no preferred direction, no axis, no center. The cosmic web itself is a fascinating structure. Galaxies aren't randomly scattered through space. They're organized into filaments, thin threads of galaxies that stretch for hundreds of millions of light years. Where filaments intersect, you find galaxy clusters, dense concentrations of thousands of galaxies. Between the filaments are voids, enormous empty regions that can be hundreds of millions of light years across. This structure looks complex and non-uniform at scales of tens or hundreds of millions of light years, but at larger scales, it averages out. The filaments and voids are randomly distributed. There's no superstructure, no pattern that extends across the entire observable universe. The universe is uniform when you look at large enough scales. There are some puzzling anomalies that have generated considerable scientific debate. The CMB has a few features that seem to break perfect isotropy. There's a slightly cold spot in one direction about 10 degrees across, that's colder than average by about 70 microkelvins. There are alignments between certain patterns in the CMB that might not be random. The quadrupole and octupole moments of the CMB seem to be aligned with each other and with the ecliptic plane of our solar system, which is strange because the CMB shouldn't know anything about our solar system. Cosmologists are still debating whether these anomalies are real features of the universe or statistical flukes. When you measure thousands of properties of the CMB, some of them will appear unusual just by chance. It's like flipping a coin 1,000 times. You'll get some runs of heads or tails that look non-random, but they're just expected statistical fluctuations. Even if these anomalies are real, the tiny effects, they don't indicate a cosmic center. They might indicate some subtle asymmetry in the very early universe, or some unknown physical process, or simply the limits of our statistical methods. The universe is still isotropic, 2 to then 1%. The cosmological principle holds to very high precision. Scientists don't simply assume the cosmological principle is true. They actively try to break it. Every new telescope, every deeper survey, every more precise measurement is an opportunity to find evidence that the universe isn't uniform after all. Astronomers search for patterns in galaxy distributions. They look for anomalies in the CMB. They test whether the expansion rate is truly the same in all directions. They examine whether distant supernovae behave the same way in different parts of the sky. If the cosmological principle were wrong, the consequences would be enormous. Our entire framework for understanding the cosmos would need revision. The equations of cosmology assume uniformity. If that assumption failed at some level, we'd need new mathematics, new models, perhaps entirely new physics. The stakes are high, which is why scientists keep testing. So far, every test has confirmed uniformity. But scientists keep looking, keep pushing, keep searching for any deviation. That's how science works. You don't protect your assumptions, you attack them. You try your hardest to prove yourself wrong. And if your theory survives the assault, you gain confidence that it's actually true. Now, let's talk about what the cosmological principle implies for the shape and extent of the universe. This is where things get truly mind-bending, where our everyday intuitions about geometry completely break down. The universe could have one of 3 possible large-scale geometries. It could be positively curved, like the surface of a sphere. It could be negatively curved, like a saddle shape. Or it could be flat with 0 curvature, like an infinite plane extending forever in all directions. Positive curvature means that parallel lines eventually converge. If you drew 2 lines that started out parallel and extended them far enough, they would meet. This is hard to visualize in 3 dimensions, but think about the surface of a sphere. Lines of longitude on Earth start out parallel at the equator, running due north, but they converge at the poles. They're parallel locally but meet globally. In a positively curved universe, space itself curves back on itself. If you traveled in a straight line far enough, you'd eventually return to your starting point, like circumnavigating a globe. Such a universe would be finite in volume but have no edges or boundaries. You could travel forever without hitting a wall, but you'd eventually come back to where you started. Negative curvature means parallel lines diverge. Extend them far enough, and they get farther and farther apart forever. A saddle shape has negative curvature. The surface curves up in one direction and down in the perpendicular direction. In a negatively curved universe, Space spreads apart as you travel through it. Such a universe would be infinite, extending forever in all directions without ever curving back on itself. Zero curvature, flatness, means parallel lines stay parallel forever. They never converge and never diverge. This is the geometry we learn in school, the geometry of everyday experience. Euclidean geometry. In a flat universe, space extends forever in all directions without curving. It's infinite in extent. The curvature of the universe is determined by its total density of matter and energy. There's a critical density, a specific value that corresponds to a flat universe. This critical density is about 5 or 6 hydrogen atoms per cubic meter, averaged over all of space, including the vast voids between galaxies. If the actual density is higher than the critical density, the universe has positive curvature. If the density is lower, the universe has negative curvature. If the density exactly equals the critical density, the universe is flat. Observations, particularly of the CMB, have measured the universe's density with high precision. The CMB contains information about the curvature because the size of the fluctuations depends on the geometry of space. Sound waves in the early universe created patterns of hot and cold spots. The apparent size of these spots depends on how space curves between the CMB and us. The result is remarkable. The universe is flat within the precision of our measurements. The density is within about 1% of the critical density. As far as we can tell, parallel lines stay parallel forever. Space does not curve back on itself. A flat universe, if it's also homogeneous and isotropic, could be infinite. It could extend forever in all directions without any boundary. This is the simplest interpretation of a flat universe, and many cosmologists take it seriously. An infinite universe has no center and no edge by definition. Every point is equivalent. There's no boundary to mark the center from. Alternatively, a flat universe could have a strange topology that makes it finite but without edges. Imagine taking a sheet of paper and rolling it into a cylinder. The cylinder has no edges in the direction you rolled. It's finite in one direction, but the edges connect. Now imagine rolling the cylinder into a torus, like a donut shape. The torus has no edges at all, but it has finite area. You can walk around it and come back to where you started. A flat universe could have a similar topology, where if you traveled far enough in one direction, you'd end up back where you started. The universe would be like a 3-dimensional version of a torus, finite but without edges. In such a universe, you might even be able to see the back of your own head if you looked far enough in any direction, because light would travel all the way around and return. We don't know whether the universe has this kind of strange topology. If it does, the universe would have to be very large, larger than the observable universe, or we would see repeating patterns in the CMB. We'd see the same distant regions multiple times in different directions. We've looked for such patterns and haven't found them, which means either the universe is infinite or it's finite but larger than we can observe. Such a universe would still have no center. Every point would be equivalent. There would be no edge because any direction you traveled would eventually bring you back. The topology would be strange, but the cosmological principle would still hold. What we do know is that the universe is homogeneous and isotropic on large scales. Whatever its ultimate shape or extent, it has no preferred center. Every point is equivalent. The laws of physics are the same everywhere. The density of matter is the same everywhere. The expansion rate is the same everywhere. Homogeneity and isotropy rule out a center. Let me address a common misconception here. Some people think that if the Big Bang happened 13.8 billion years ago, the universe must be a sphere 13.8 billion light years in radius, with us at the center. After all, that's how far light could have traveled since the beginning. The Big Bang happened at one location, and everything has been spreading out from that location for 13.8 billion years. So we must be in a sphere of that radius. But this reasoning is flawed for several reasons. First, the universe has been expanding. Light that was emitted near the beginning has been traveling through expanding space. The objects that emitted that light are now much farther away than 13.8 billion light years because space has stretched since the light was emitted. The observable universe is actually about 46 billion light years in radius, not 13.8 billion. Second, and more importantly, the cosmic horizon is not a physical edge. It's just a limit on our observations. There's nothing special about the boundary of the observable universe. Galaxies just beyond that boundary are no different from galaxies just inside it. They're just too far away for their light to have reached us yet. The boundary is about us and our limitations, not about the structure of the universe. Third, and most crucially, the Big Bang didn't happen at a location. It happened everywhere. Every point in space was the location of the Big Bang. The expansion has been happening everywhere, at every point since the beginning. There's no central point from which everything is spreading. The observable universe is centered on us, but that's a consequence of perspective, not physics. Every observer has their own observable universe, centered on themselves. It's like the horizon you see from a mountaintop. You're at the center of your horizon, but that doesn't mean you're at the center of the Earth. The horizon is observer dependent, and so is the observable universe. The universe itself, as opposed to the observable universe, is homogeneous and isotropic. No point is special. No point is the center. The cosmological principle applies everywhere to every observer throughout the cosmos. Now, let me discuss how the cosmological principle connects to the laws of physics. One of the deepest principles in physics is that the laws of nature are the same everywhere. Gravity works the same way on Earth as in a distant galaxy. Atoms behave the same way here as anywhere else in the cosmos. The speed of light is the same everywhere. The strength of the electromagnetic force is the same everywhere. This uniformity of physical law is closely related to homogeneity. If the laws of physics were different in different places, the universe wouldn't be homogeneous. Different regions would behave differently. Stars would shine with different brightness. Atoms would have different sizes. Chemistry would work differently. The universe would be a patchwork of different physics. But all observations confirm that the laws of physics are universal. We can see spectral lines from distant galaxies, and they're the same lines we see in laboratories on Earth. The ratios of wavelengths are identical. The patterns are identical. Hydrogen in a galaxy 10 billion light years away behaves exactly like hydrogen in a tube in a physics lab. This tells us the laws of physics haven't changed over billions of years and billions of light years. The uniformity of physical law also connects to the absence of a cosmic center. A center would be a special place. Perhaps the laws of physics would be different there. Perhaps gravity would be stronger, or the speed of light would be different, or atoms would behave differently. But we see no evidence of any such place. The laws of physics are the same everywhere we look, in every direction, out to the farthest galaxies we can observe. There's no hint of a special location where things work differently. Some speculative theories propose that the universe might have regions with different physical laws. In the multiverse hypothesis, our universe might be one of many, each with different physical constants. The strength of gravity, the mass of the electron, the speed of light might vary from universe to universe. Within our universe, the laws would be uniform, but other universes might have different laws. These ideas are at the frontier of theoretical physics and are extremely difficult to test. We have no way to observe other universes, if they exist. We can only observe our own universe, and within our universe, the laws of physics appear to be uniform. Even if other universes exist with different physics, this wouldn't create a center within our universe. There would just be different universes with different properties, none of them more central than the others. Our universe would still be homogeneous and isotropic, with no center, just as it appears to be. The cosmological principle has profound implications that extend beyond pure science. By establishing that no location is privileged, it shapes our understanding of our place in existence. It tells us we're not at the center of creation, not in a special place chosen by cosmic design. We're in an ordinary region of an ordinary galaxy in an ordinary supercluster in a universe that looks the same from everywhere. We'll explore the deeper philosophical dimensions of this truth in our final section, after we've examined what lies beyond the observable universe and what the future holds for our centerless cosmos. The cosmological principle, homogeneity and isotropy, is the foundation on which modern cosmology rests. It tells us that the universe is the same everywhere and the same in all directions. It rules out a cosmic center. It makes every location equivalent, and it's supported by the most precise observations we've ever made. From the cosmic microwave background to galaxy surveys to measurements of the expansion rate, the universe has no center because it has no special places. Every point is like every other point. Every direction is like every other direction. This uniformity is not a limitation, but a liberation. It means the universe is comprehensible, predictable, governed by laws we can discover and understand. It means we can look out at the cosmos and see not chaos, but order, not confusion, but clarity. We've established that the expansion of the universe looks the same from every vantage point. We've explored how space is uniform at large scales, the same everywhere and in all directions. We've seen why there's no special location, no origin point, no cosmic middle. But now let's push further into the deepest implications and most profound questions. What can we actually observe? What lies beyond the edge of our vision? What do we still not understand? And what does all this mean for our place within this vast, centerless cosmos? Let's start with the observable universe, the portion of the cosmos from which light has had time to reach us since the Big Bang. The universe is about 13.8 billion years old. You might think this means we can see 13.8 billion light years in every direction. Light travels at 1 light year per year by definition, so in 13.8 billion years, it should travel 13.8 billion light years. But the universe has been expanding the whole time. Light that started its journey near the beginning of time has been traveling through stretching space. The objects that emitted that light have been carried away by the expansion, even as their light traveled toward us. By the time the light arrives, the objects are much farther away than when the light was emitted. The result is that the observable universe is much larger than 13.8 billion light years. The most distant regions we can observe are currently about 46 billion light years away. This gives the observable universe a diameter of about 93 billion light years. That's the size of the cosmic sphere from which light has reached us, accounting for the expansion of space during the light's journey. Within this sphere, we estimate there are about 2 trillion galaxies. Each galaxy contains anywhere from millions to trillions of stars. The total number of stars in the observable universe is estimated at around 200 billion trillion. That's a 2 followed by 23 zeros. Each of those stars is a nuclear furnace burning hydrogen into helium, many with planets orbiting them, scattered through a volume of space so vast that crossing it at light speed would take 93 billion years. Now, here's a subtle but crucial point. We are at the center of the observable universe. This is true by definition. The observable universe is defined as the region from which light has reached us. That region is necessarily centered on us because it's defined by light traveling to us. But as we've established, this doesn't make our position cosmically special. Every observer is at the center of their own observable universe. The observable universe is perspective dependent, following each observer like a shadow. Think of it like a fog. If you're standing in a dense fog, you can only see a certain distance in any direction. You're at the center of your visible region, but that doesn't mean you're at the center of the landscape. Someone else, standing in the fog a mile away, is at the center of their visible region. Everyone is at the center of what they can see, but no one is at the center of the fog itself. The observable universe works the same way. We're at the center of what we can see because seeing is defined by light reaching us. But the universe itself extends far beyond what we can see, and within that larger universe, our position is not special. Beyond the observable universe, the universe continues. We can't see it, but we have every reason to believe it's there. Galaxies exist beyond our cosmic horizon. Space extends beyond what light has had time to traverse. How far beyond? This is one of the deepest questions in cosmology, and the honest answer is that we don't know. The universe could extend for a finite but enormous distance beyond what we can see. It could be 10 times larger than the observable universe, or 1,000,000 times larger, or 1,000,000,000 times larger. Current observations can't distinguish between these possibilities. All we can say is that if the universe is finite, it's much larger than what we can observe. Alternatively, the universe could be infinite, extending forever in all directions without any boundary at all. This is actually the simplest interpretation of a flat universe, which is what observations suggest we live in. An infinite universe would have no center and no edge by definition. Every point in an infinite universe is surrounded by infinite space in all directions. There's no boundary, no middle, no special location. In an infinite universe that's the same throughout, every possible configuration of matter occurs somewhere. There are only a finite number of ways to arrange particles in a finite region. If the universe is infinite, it contains infinitely many regions. By probability, some of those regions would be essentially identical to our observable universe. There would be other Earths, other solar systems, other versions of you. This isn't mysticism. It's straightforward probability applied to infinite space. The distances involved would be incomprehensibly vast. The nearest exact copy of you might be farther away than any distance we can meaningfully express. But in an infinite universe, that copy would exist somewhere. What about the Big Bang? Wasn't that the origin of everything? Wasn't that the center from which everything emerged? As we established earlier, the Big Bang was not an explosion at a single location. It was the beginning of expansion everywhere simultaneously. Every point in space was the location of the Big Bang because in the beginning, every point that exists now was compressed together in an almost unimaginably hot and dense state. There was no pre-existing empty space that the universe exploded into. Space itself began and began everywhere at once. There was no outside, no surrounding void, no center of the explosion. This is fundamentally different from any explosion you can imagine, and it's why asking where the Big Bang happened is the wrong question. It happened everywhere. Our understanding of the very first moments remains incomplete. General relativity predicts a singularity at the beginning, a point of infinite density where the equations break down. But most physicists believe this singularity is an artifact of our incomplete understanding. We need a theory of quantum gravity to understand what really happened at the beginning, and we don't have a complete theory yet. Some people ask what caused the Big Bang or what came before it. These are natural questions, perhaps the most natural questions of all, but they may not have answers in the form we expect. If time itself began at the Big Bang, then there was no before for a cause to exist in. Asking what came before the Big Bang might be like asking what's north of the North Pole. The question seems sensible. It uses words that have meaning in other contexts, but it assumes a framework that doesn't apply. There may be nothing before the Big Bang because time began at the Big Bang. The question might be meaningless, not because we don't know the answer, but because there is no answer to know. There are speculative theories about what might have preceded the Big Bang. Perhaps our universe budded off from another universe through eternal inflation. Perhaps there's a multiverse of universes, each with its own Big Bang. Perhaps time is cyclic. These are fascinating ideas, but they're beyond what we can currently test. They remain speculation about realms we cannot observe. Let me now turn to the far future of the universe, because understanding where the cosmos is heading helps illuminate why the centerless nature of reality is so fundamental. The universe is expanding, and that expansion is accelerating due to dark energy. Distant galaxies are being carried away from us, faster and faster. Eventually they'll cross a threshold where their recession velocity exceeds the speed of light. When this happens, the light they emit can never reach us. They pass beyond our cosmic horizon and are lost to us forever. This process is already happening. Galaxies that are currently visible to us will eventually disappear from view as the expansion carries them beyond our horizon. We can still see them now, seeing light that was emitted billions of years ago. But new light they emit will never reach us. They're fading into the unobservable. In the far future, trillions of years from now, this process will be largely complete. Almost all galaxies will have been carried beyond the cosmic horizon. The only objects still visible will be those in our local group, the collection of over 80 galaxies gravitationally bound to the Milky Way, though most are small dwarf galaxies. These galaxies are close enough that their mutual gravity overcomes the cosmic expansion. They'll stay together while everything else disappears. The Milky Way and Andromeda will merge in about 4.5 billion years, along with the other galaxies in our local group, forming a single giant elliptical galaxy. Astronomers have nicknamed this future galaxy Milkomeda or Milkdromeda. It will contain over 1 trillion stars, the combined stellar populations of all the galaxies that merge to form it. Future astronomers in that distant era, trillions of years from now, will look out at the universe and see nothing beyond their own galaxy. The rest of the universe will have been carried away by expansion, beyond any possible observation. The sky beyond their galaxy will be black and utterly empty. Those future astronomers might conclude that their galaxy is the entire universe. They would have no way to know that they're actually part of a vast cosmos, stretching for trillions of light years or more. The evidence of other galaxies will be gone. The evidence of the Big Bang will be gone too. The cosmic microwave background will have been redshifted to undetectable wavelengths, stretched by the expansion into radio waves so long and faint that no instrument could detect them. Those future observers would live in ignorance through no fault of their own. They would be intelligent beings, perhaps far more intelligent than us, using the best instruments they could build, following the scientific method faithfully. But the universe would have hidden its own history from them. The evidence that revealed the truth to us will no longer exist. This is a sobering thought. We happen to live at a privileged time in cosmic history. Not a privileged place, because there is no privileged place, but a privileged era. The universe is old enough for galaxies to have formed and life to have evolved, but young enough that we can still see the evidence of the Big Bang and the large-scale structure of the cosmos. We can observe billions of galaxies. We can detect the cosmic microwave background. We can piece together the history of the universe from its first moments to the present day. This window won't last forever. The universe is gradually erasing the evidence of its own history. The expansion is carrying galaxies beyond our horizon. The cosmic microwave background is fading. In the far future, the cosmos will hide its true nature from whatever observers remain. We are lucky to be here now, able to see the universe as it truly is. For all we've learned, profound mysteries remain. We don't know what dark energy actually is. We've named it, measured its effects, calculated that it makes up about 68% of the universe's energy content, but we have no idea what it is. It could be a property of space itself, what physicists call a cosmological constant. It could be a new kind of field pervading all of existence. It could be something we haven't imagined yet. After more than 2 decades since its discovery, dark energy remains one of the deepest mysteries in all of science. We don't know what dark matter is either. We know it exists because we can see its gravitational effects. Galaxies rotate too fast. Galaxy clusters hold together too tightly. The cosmic web has too much structure. Something is providing extra gravity, and that something outweighs all the normal matter in the universe by a factor of 5. But we've never detected a dark matter particle directly. We don't know what it's made of. It could be a new kind of particle. It could be something stranger still. We don't know if the universe is truly infinite or merely vast beyond our ability to measure. We don't know what happened at the actual moment of the Big Bang, when our theories break down and the equations give nonsense answers like infinite density and zero volume. We don't know why there's something rather than nothing, why the universe exists at all. We don't know if we're alone in this centerless cosmos. The universe contains trillions of galaxies, each with billions of stars, many with planets. The ingredients for life seem common, but we found no evidence of life beyond Earth. No signals, no visitors, no artifacts. Either life is rare, or intelligence is rare, or technological civilizations are rare, or they're out there but we haven't found them yet. We don't know which. These mysteries are not failures of science. They're invitations. They're the frontiers where the next discoveries wait. Every generation of scientists has faced mysteries that seemed insurmountable, and every generation has pushed the boundaries further. The mysteries we face today will yield to investigation, just as the mysteries of the past have yielded. And new mysteries will take their place, deeper and stranger than anything we can currently imagine. What does it mean for us, psychologically and philosophically, that the universe has no center? For some people, this might feel diminishing. We're not at the center of anything. Our place in the cosmos is ordinary, unremarkable, no different from countless other locations scattered through the void. The dreams of ancient peoples who place themselves at the cosmic center with everything revolving around them have been definitively refuted by observation. The history of astronomy has been a history of displacement in this sense. First, we learned Earth wasn't at the center of the cosmos. Then we learned the sun wasn't at the center of the galaxy. Then we learned the galaxy wasn't at the center of the universe. And finally we learned there is no center at all. Each step moved us further from any special position. But there's another way to see this that transforms apparent diminishment into liberation. The absence of a center means every place is equally significant. No location is privileged above any other. The laws of physics that govern our world govern every world. The atoms in your body follow the same rules as atoms in the most distant galaxies we can observe. This universality is profound. You are not at the center, but neither is anyone else, anywhere in the universe. The cosmic playing field is perfectly level. No observer has a better vantage point. No location has special access to truth. Everyone everywhere is in the same situation, looking out at the same cosmos, seeing the same patterns, discovering the same laws. This makes science possible on a cosmic scale. If the laws of physics were different in different places, we could only understand our local region. But because the universe is the same throughout, what we learn here applies everywhere. The chemistry that enables life on Earth could enable life throughout the cosmos. The physics we discover in laboratories on our small planet governs processes in galaxies billions of light years away. The absence of a center also carries a kind of moral weight. If no place is privileged, then the perspective of any intelligent being anywhere in the universe is equally valid. Their questions are as important as ours. Their understanding is as meaningful as ours. We're all in this together, scattered throughout a centerless cosmos, each observer equivalent to every other. If intelligent life exists elsewhere, those beings are looking at the same universe we are. They see the same expansion. They measure the same cosmic microwave background. They discover the same laws of physics. They reach the same conclusion we have, that the universe has no center, that every location is equivalent, that no observer is special. In a strange way, the centerless universe connects us to any other minds that might exist. We share the same cosmos, governed by the same rules, lacking any center that would make one perspective more valid than another. We are companions in understanding, even if we never meet, even if we never communicate, even if we're separated by distances so vast that light itself would take billions of years to cross. Let me reflect on how we came to understand all this. The knowledge I've shared didn't come from revelation or intuition. It came from human investigation, from centuries of patient observation, careful reasoning, and rigorous testing of ideas against reality. A few centuries ago, humans thought Earth was the center of a small cosmos. The stars were lights fixed to a celestial sphere just beyond the planets. The universe was cozy, comprehensible, human-scaled. You could imagine reaching up and touching the dome of heaven. Now we know the universe is vast beyond imagination, containing trillions of galaxies across billions of light years, with no center, no edge, no preferred place. We know it began in a hot, dense state 13.8 billion years ago, and has been expanding ever since. We know it's governed by physical laws that are the same everywhere. Laws that we have discovered through experiment and observation. This transformation in understanding is one of humanity's greatest achievements. We didn't just learn new facts, we developed new ways of knowing, new methods for testing ideas, new tools for observing the cosmos. The scientific revolution that began a few centuries ago has completely transformed our picture of reality. And we're not done. Every generation of scientists builds on what came before. The discoveries of today become the foundations of tomorrow. New telescopes are being built that will see further and more clearly than anything we have now. New theories are being developed that might explain what we don't yet understand. The story of cosmic understanding is still being written. The universe has no center. This is strange, counterintuitive, hard to fully accept at a gut level. Your brain evolved to understand centers and edges, origins and destinations. Every object you encounter in daily life has a middle. Letting go of this intuition requires effort, requires thinking carefully, requires building new mental models. But once you do, something beautiful emerges. The cosmos becomes more wonderful, not less. It's not a sphere with a somewhere off to the side, displaced from importance. It's not an explosion with debris flying from some distant origin. It's a vast expanse of space, perhaps infinite, stretching in all directions, expanding everywhere, governed by the same laws throughout. Every point is equivalent. Every observer is at the center of their own observable universe. Every perspective is equally valid. You are made of atoms that were forged in stars that died billions of years ago. Those atoms drifted through space for eons, eventually coming together to form the Earth, and then to form you. You are the cosmos looking back at itself, trying to understand its own nature. The universe has no center, but it has you in it, wondering about these things. Out of all the possible arrangements of matter, out of all the ways atoms could combine and recombine through the vast stretches of cosmic time, some arrangements have become aware. Some have started asking why. Some have built telescopes and measured redshifts and figured out that space is expanding and that nowhere is special. You are one of those arrangements, standing on a planet, orbiting a star, in a galaxy among trillions, in a universe without a center. Your position is ordinary in cosmic terms, but your ability to understand that position, to grasp the true nature of the cosmos, is extraordinary. Consciousness might be rare. Understanding might be rarer still. You are something precious, matter that knows it exists. When you go outside tonight and look up at the sky, if the sky is clear and dark enough, you might see the Milky Way stretching overhead like a river of light. That band of light is the combined glow of billions of stars, all part of our galaxy. Beyond those stars, invisible to the naked eye but there nonetheless, are other galaxies, billions of them, trillions of them, spread through an expanding space that has no center. Every one of those galaxies is at the center of the expansion from its own perspective. Every one is equivalent to every other. The universe plays no favorites. It doesn't privilege any location or any observer. And you, standing on your small planet, looking up at the cosmos with wonder, are at the center too. Not the center of the universe, because there is no such thing. The center of your observable universe. The center of your view of reality. as valid as any other observer's view, as central as any other position could be. This is what the centerless universe means. Not that you're unimportant, but that everyone is equally important. Not that your position doesn't matter, but that every position matters equally. Not that there's no meaning, but that meaning is distributed throughout the cosmos, everywhere and nowhere, just like the center itself. The universe has no center. This fact is one of the most important truths we've discovered about reality. It tells us that the cosmos is fair, uniform, comprehensible. It tells us that what we learn here applies everywhere. It tells us that we're not special, but also that no one else is special either. That story is more wonderful than any mythology humans ever created. More profound than any ancient cosmology. More beautiful than any picture with Earth or the sun at the middle. It's the story of a universe that simply exists, expanding eternally into itself, governed by physical laws that make no distinction between here and there. We are not at the center of the universe. We are part of a universe where center has no meaning. And that is, in its own way, the most extraordinary place to be. Thank you for joining me on this journey through one of the deepest ideas in cosmology. If you found this exploration valuable, a like or subscribe would help bring more of these journeys to others who share your curiosity about the cosmos. And remember, the next time someone asks you where the center of the universe is, you can tell them the truth. Everywhere and nowhere, all at once, every point equally central and equally peripheral. A universe that has no center because it needs none. Good night, and sleep well knowing that, in a centerless cosmos stretching perhaps infinitely in all directions, you are exactly where you belong.